want, we can revisit this.
Actually, that would be good because Sunday we have GA5 submission. No?
Right, okay. Okay, I'll go ahead with week 5, okay? Okay. We'll start with week 5. I will give a just about week 5 once, and then we can solve some problems based on it. We can start off with some problems, okay? Right. Till now, what we have seen, most the bigger topics are Laplace. We have seen that can be used later in any other weeks. It's a mathematical tool, and we have studied about transient responses, steady state responses, transfer functions mainly. What else? Convolution, mechanical or electrical, rotational, mathematical, design or any system, how to design or represent the system, either it is a mechanical system or electrical or rotational system that we studied. So these are all the topics we have broadly covered in the first 4 weeks. That this week 1 to week 4, you will get it for quiz. This will be covered for quiz 1. Okay, right. In week 5, with respect to all the things we learned, we are going to apply this on the coming weeks, and few other new tools also we'll be studying. Stability we studied, that will be helpful. So this we'll try to apply some of this tools in this coming weeks. So this week 5 covers analysis of feedback systems. So in this, the fundamental thing, let me, okay. So, till now we have studied stability. We know what it is, what stability is, and why we are using that, right? One minute, my pen is not working. Okay, we have seen this. We have to think of it. I don't have. Okay. I'm sorry for the interruption. So till now we have seen what is stability, and we are going to see what is tracking and regulation and how well it is going to help us in studying any system. Okay, so we will analyze each of these requirements in terms of stability or in terms of tracking or regulations to help the system to be controlled or to give a desired response how we need. But most probably this will be useful only for LTA system. Okay, from now on, our goal is to design a controllers to achieve our requirements to get the desired response. So we have seen there are, for any system, there are classifications called open loop and the closed loop. Where closed loop involves feedback, open loop doesn't have any feedback. So by taking the output and giving it to the system, giving the knowledge of this output back to the system, we will be able to control the system better than the open loop system. Right. We'll start off with this open loop control. In open loop structure, there won't be any point to control. We will just give some input and expect the system to give some output. If the system is proper or if it is ideally well, it will give a desired response, but in a real time system we cannot expect that to happen. For example, some examples they have given is washing machines. We'll just give current and it will give a mechanical power. Traffic lights, we'll just program the lights to turn on at every particular interval of time. It doesn't care about how people are responding to it. It just goes on and on according to the program, right? So these are all some examples for the open loop system. And the main thing is open loop systems are heavily prone to disturbances. If I have, if I give some input to my system, and first criteria is it should be naturally good to give a desired response. The second thing is, even if it is naturally good, it should be able to reject the disturbance. It should reject the disturbances. But in open loop system, you don't have any provision to control this factor, disturbances. How will the disturbance is going to affect the system and what are all the effects of this disturbance? You cannot understand that. So it's just a out of control system. You cannot do anything about it to avoid this disturbances or the things that is that this disturbance is making on your system. So the output will be largely affected by the change in the system's parameters. Some example they have given is electronic circuit that is affected due to the change in circuit parameters. For example, change in impedance or change in its capacitance due to this environmental conditions like temperature. So some materials are prone to change in temperatures. If it is designed to work well in particular temperature, if it exceeds or reduces, it might not do its work, right? So this kinds of system we cannot do anything about it. It's out of control. So here, what they are calling it as a tracking error is okay. I'm considering an example here. First of all, they're giving a thermal control system where they have mentioned the system information in terms of some numerical input, where this is a transfer function. This represents the poles, there is no zero, and the poles are in -1, and okay, another will be 1 by 10, right? -1 by 10. So these are all the two poles of the system. Given for the given thermal control system. The goal is to design a controller to track the reference input. For example, if I give a reference input 5 degrees Celsius, I am expected, if this is a 5 degrees Celsius input I am giving, I am expected to make the output behave in the same way, at least after the transient response. It should track the input. Tracking means the output should be equal, more or less equal to the input or the reference input I am giving. This is the goal of the system, and I want to design a controller to make the system work in this way. So the reference input I am giving is it's in terms of ramp signal with a slope of 30 degrees Celsius, and I'm giving it for a duration of 30 seconds. And this steady state, after some time, it is going to reach a 300 degrees Celsius value. So that is going to be the steady state. If I want to make a control for this closed loop system, the idea behind this is to excite the system with an input step of 0.3, because okay, right. So we have this 1000 in the numerator, right? If I want to make the steady state value goes to 300, what changes I can make to this 1000 to make it 300? You have to think in that way. Just 300 by 1000, right? So this will give you 0.3. So you have to make an input such that its step size or the continuous size, this is since it is going to be a continuous signal, we are considering it as a step signal. So this should be 0.3. That's how we are calculating it. I think we have discussed this previously. Okay, right. So when I simulate this transfer function of 1000 by s plus 10, 10s plus 1. So if I simulate this example and given this is my reference signal, when I said that this will increase at a rate of 30 degree per centigrade per second, and at steady state after some time, after 30 seconds, it is going to reach 300 degrees Celsius. Right. So this is the red line is the reference input I am giving to my system, and I'm expecting my system to reach this point nearly, however closely it is possible. I have to make the system to work like that so that I can consider my tracking is very good. If it tracks it very well, I can say we have system designed a system controller very well. Right. So this is my objective. Right. I will come back to this. So what I'm going to do is I'm going to apply this simple control so that the output response, if you can see here the blue color, it's able to track after some time. It is not tracking properly during the transient period. And after this 30 seconds, when it reaches the steady state, it tends to move towards the reference input so that you can see the difference between this and this. That's why we have plotted this tracking error. It's a difference between these input or reference input and the controlled output. The output response after implementing this control signal, this one. So this is the error between that, and you can see after 30, the error tends to decrease. So if it goes to 0, nearly 0, I would say we have designed a very good controller. So this is what the this is where the measurement or quantitative analysis of the control parameters lies in. So the same thing when it comes to a regulation, till now we have see about tracking. And when it comes to regulation, these are similar topics, but you would find a little bit difference between that. When I say tracking, I am just expecting my output to track my input. That's it. When I say regulation, the output should maintain a constant value in spite of disturbance. Even though if I apply a disturbance to my system, some in terms of sine wave or any other disturbances I'm including in my system, my output should not jitter. Like it should be stable. How well it is stable, that's how well the regulation is. So for example, I'm traveling in a straight road and all of a sudden there is a bump. So even though if I travel at a high speed and hitting this bump, if I'm able to regain my control of my vehicle, then I can say I'm good at regulation, or my vehicle is or the control system here. I'm the control system, right? So I'm regulating it very well. In spite of any disturbances, if the system is able to gain its control back, or if it is not giving any unstable or improper output, then you can say your controller design is regulation of this controller design is very well designed. Right. So it till now we haven't spoken about any disturbances. Now, since we are speaking about the regulation, the another term DFS or NFS, it's coming into the picture. In a control system, if this is a RFS, that is an input, and this is the transfer function or your feed forward gate, and it is this output YFS. I'm taking this back into the feedback and giving it to here. So usually we will measure error here, and usually we will include disturbances here. Okay. Right. So this is another example of for tracking. In this regulation. In this example, they are taking the same example from above. The same system, there is a temperature control system. Instead of fixing the goal to track my reference, I am fixing the goal that it should track the reference in spite of disturbances. Even though I am giving some disturbances kind of any keeping an ice inside the room, or blowing and hot air inside the room, kind of any changes or any external disturbance I am giving, the system or the AC, let's consider a temperature control system, it should behave properly according to the nature of that room, right? So this is another example where you can see here, if we simulate the same thing, the black line is the error without any disturbance. Just the same error plot they are tracking, they are plotting for the regulation here. This is the error without disturbance, where you can see it is almost zero, where you can say that it's tracking very well after the 30 seconds that time we have considered. And but if we introduce some disturbance, it is the error is getting increased. It is not being controlled properly. So this is this red color is the reference input. Here we are considering a step reference, and the blue line is the output without disturbance, where it is tracking very well after some transient responses. But if I introduce some disturbance, that output is not so tracking well. So these are some kind of examples that you can encounter, but by incorporating more good controllers like PID controllers or any other updated controllers, MPC controllers, we will be able to manage this disturbance very well. So you should design a proper control system to reduce this abruption or any change in the output tracking in spite of the disturbances. So this concepts, I think we have already visited this. Stability, how well, how is the system stable based on the poles, location of the poles, and we have already seen this RHS of the S-plane, then it is not stable. Unstable pole remains. If there is a pole that is in the right half of the S-plane, it's inherently unstable and we cannot do anything about this. Even without disturbances, it is going to give unbounded input output. With disturbances, it is going to increase that behavior. It is not going to be under control. And you should,
Ma'am,
yeah.
can you explain the last point of the previous slide?
Oh, okay, right. If we have already seen this, right, location of poles, how it is going to affect the system. So here, I'm going to show this in red color, right? Okay, this is LHS, this is RHS. So whenever, consider this is a S-plane, this is the origin, and sigma and j omega. S-plane will be mentioned, represented using the sigma plus j omega, where it involves the real number and the complex number. So this plane, the x-axis will represent the real number, y-axis will represent the complex numbers. So whenever there are poles, poles means if I represent the transfer function, whatever value that is in the numerator is called 0, whatever is there in the denominator is called poles, or factors of those characteristic equation, right? Poles are similar to roots of the system, right? Whenever it is located in the left half of the S-plane, for example, in the negative side of the graph, -2, -1, minus 0.01, kind of all those negative poles or negative roots of the system, we call that roots as stable, since it is lying on the left half of the S-plane. All this area belongs to left of the half of the S-plane. Whenever it is lying on the right half of the S-plane, positive numbers, positive real numbers or positive complex numbers, plus 2 plus j omega, 2 plus 2 j omega, all these things are 2, 10, 15, whatever ways that is positive, that we call it as unstable. This I already would have explained it. If you're not there, I will repeat it again. So when you say, for example, if I have a one pole system, S plus 1, and I have another pole system, S minus 1. Okay. So if you plot this poles, this S plus 1 will be here, minus 1. S is equal to -1. S minus 1, for this, the poles will be here, right? So let's take 2, okay, instead of for relieving the confusion. Right. If whenever I find the inverse Laplace transform for this, I would write it as e power minus t, right? Inverse Laplace transform of this would be e power 2t. So when you plot this, e power minus t would give a behavior like this, where e power 2t will give a behavior like this. So this is stable, this is unstable. So that's why we are telling whenever there is a pole that is in the right half of the S-plane, the system tend to give a unstable behavior. So even one pole in the right half of the S-plane or 3 other poles are in the left half of the S-plane, the system is unstable only. All the poles of the system should lie in the left half of the S-plane. All the poles or roots should be negative only. Right. So if a system is unstable, means if there is a pole in the right half of the S-plane, it will give this behavior. Already the system is in unstable behavior. So if I give a disturbance to the system, it is not going to enhance the behavior. It is further puts the system towards the unstable region only. So it will increase the exponential characteristics. That's what I have explained. See, however, the unstable poles remains and the slightest noise or disturbance will cause the output to grow until stopped by saturation or system failure. So until it reaches the failure or shutdown or any fatal output, it is going to give a unstable behavior only. The disturbance is not going to enhance the system when the system is inherently unstable. Is it clear or should I repeat it any part of
Ma'am,
it?
like in this last point, it is written plant shows poor response because of zero
Mm-hmm.
in right hand plane. So how can a system show poor response because of zero? Like zero means the wave is constant. It is
Okay.
not increasing. So how is it poor response?
Right. Okay. I will explain that. See, usually if transfer function, if I write, so this will be zero, this will be pole, right? All this pole, we consider this for stability. Good. This I'm writing is for open loop transfer function. So when I write a closed loop transfer function, where this is your G, right? Your G will come 1 plus GH. So automatically the G that has 0 and pole, this 0 will come here, 0 by pole, and finally this would become a pole for a closed loop system, right? This is in case of open loop transfer
Yes.
function. So open loop 0 can act as a pole in the closed loop transfer function when you find a closed loop transfer function. So even if the 0 is in the right half of the S-plane, when you when you try to design a controller using a feedback as a closed loop system, that 0 is going to affect your system stability because it is further finally it is going to be a pole of the closed loop system. This is a one point. Another point I want to make is if you consider a closed loop transfer function itself, where the 0 is in the right half of the S-plane and your pole is in the left half of the S-plane. Here, if your pole is in the left half, it won't affect your stability. Your system is inherently stable. We are not going to consider 0 for stability. But if your system is stable, but your 0 is in the right half of the S-plane, it may increase delay in your system. For example, your response may, okay, right, look like this even if it is a stable system. So this dip you are seeing here, it is because of the right hand zeros. It sometimes pull down your system. So if the pole or if the 0 isn't very far, it won't affect much. But if the 0 is very near to the origin, it start to affect your system behavior. So in this case, that's what you can get out of it. Poor response, right?
So it's like in week four also I asked about like so you also response like the
Mm.
poles are for stability. So for stable we always see that
Yeah.
should come on the left side, and for the zero if
Mm-hmm.
it's coming on the right side we can consider that our
Mm.
system will give a response in a delayed time, like
Yeah, yeah.
what he yeah
It
if
may
my
introduce
zeros
delay in the system.
Yeah, it will introduce delaying in the system if my zero is coming on the
Right
right
up
side.
of it.
Yeah, and when it's left, then means it's okay.
Ah, it's okay. Everything is in the left. It's a perfect system. You don't have to
It's a
worry about.
perfect one. Hmm.
But if it lies on the origin or in the this plane, so here,
Critical.
here, everywhere here. So it is called to be marginally stable. We don't really define whether it is stable or unstable because anytime it can go into stability or unstable region. We don't know when it is going to go there. Even a slighter disturbance can push this system
Yeah,
to unstable region.
any little change due to
Yeah,
the
yeah,
real aspects when we are making our system, it will cause
right,
instability. It will
right.
also come to the stable. It will also come to the unstable.
Mm-hmm. Yeah, right. Okay. The another important concept we can see is the sensitivity. Similar to stability, sensitivity is also a important topic in the control system. You can expect some good questions in this topic. So sensitivity is defined as how your system is going to respond to a change in the input or change in the disturbances. That is the sensitivity system. If your system is very sensitive, it will change its output response for any minimal change in the input or in the disturbances. If your system is less sensitive, it is not going to, your output response is not going to affect much. I'm not saying not going to change at all. It is not going to change much based on your change in input or in the change disturbances behavior. So we are introducing another term that is called as loop gain. Right, loop open loop gain into the system, where this open loop gain can be represented as the G of S into GC of S. So if you wonder what is this GC, it is the controller gain. For example, when you design a system, we know the standard system, right? This is R, G, Y, H, E. So this is a standard system. When you introduce a controller into the system, this will become R, C, G, Y, H, where C is the controller. So based on this error and the output, this in the output and input, the difference between this output and input will be giving back as an error. So based on this error, this C is going to change so that we will get a desired response after some runs, after some period of time. Right. So the gain of the C is called as GC. So the loop gain will be the combination of these two. Sorry, GC and G. So that's what we have written here. This we collectively called as L of S. So if I write a transfer function or the mathematical explanation of the system, I would be writing in this manner. So here what we are doing, considering a perturbed system, overall gain they have given. Okay, the L is this, and if we perturb the system gain would change. That we are calling it as delta G. So if we consider this, oh okay, right, GC into delta GS, right? This will become G into GC plus G delta G into GC. So I'm taking GC as common and putting G and delta G inside that, where delta G is a perturb. Perturb means we are introducing some disturbances over here, right? After adding the disturbance that we called as perturbed system, right? You will get, if you take this common, you will get this term L of S, where L of S is already defined here, G into G of S plus delta G into G of S. So delta L of S will be delta G into GS. It's common, it's straight away equation. So how you can write a sensitivity of a system is the transfer function. Okay. Right. Sensitivity of the system with respect to its loop gain. That's how we define as SGL is will be equal to delta L change in that loop gain by loop gain divided by change in the system response or system transfer function by original system transfer function. So if you write this, you will get G by L into delta L by delta G. Just rewriting this into this format where G and L, L is G into GC into delta L, it is here. Delta G into GC divided by G into GC, right? It's just an explanation where, or a parametrical expression where you can find how well the system is sensitive, or how your system is sensitive to any changes to your loop gain. Loop gain changes is because of the disturbances or some input changes also. Okay, this is a closed loop structure we are considering. So D is the disturbance or noise. Right. I have already told this. If anyone could remember, can you tell me what is the difference between disturbance and noise? Is there any disturbance difference between these two, or both are interchangeably usable?
Noise, what we are getting at the output, and disturbance, what we are giving at the input.
Okay, vaguely correct, but it should be refined.
Means like if I'm giving it to the system, like perturbation, disturbance, what you said, and
Mm-hmm.
noise, what at output, if I'm getting any other waves, like vibrating or something other than my solution, that's called noise. Noise we are getting at output, and disturbance are what we are giving uh, to the input.
Okay, I can say this as disturbance. Most probably, we will consider in terms of process or the system.
Yeah,
Noise we will deal in terms of measurement or senses,
yeah.
right?
So
If
processing what I said at input and measurement at output. So
right,
yeah.
good. So if the system, if there is, for example, uh, I'm thinking of an example. They can easily represent this. Okay, this is a way where I am traveling in a car here. Okay, so I'm traveling at a speed of 30 kilometer per hour, for example. So until there is any wind or it's a very natural way, so I'm traveling at this constant speed, 30 kilometer per hour. So sometimes there is some wind or some disturbances, external disturbances, some force wind or some storm comes, then it affects my system speed. Whatever speed I'm going, if I'm giving the same input, I won't be able to travel at that speed, right? So my speed gets slightly reduced, for example, 28 or 29. So this is the effect of the disturbance here. But when I measure, even if I go at a 30 kilometer per hour, even there is no wind or in the presence of wind, if my speedometer is showing 38 kilometer per hour, okay, so in this case I'm replacing my speedometer. Now it is showing 30 kilometer per hour. So how will you differentiate this? So in spite of any external disturbances, if the output changes, then that is called disturbances. But if you change the sensors, it should not change. Like, it's a process, it's a output of the process. If I change the sensor, if it gives a different result, then I can say that is a noise. It is present in the sensor, not in the process. So this is the basic difference between the disturbance and noise. So if it is a disturbance, changing your sensor doesn't change your output. If it is a noise, it may present in that particular sensor in terms of measurement noise, or you may do any error while measuring those things. For example, tachometer, we used to do those experiments in BTech projects, right? In mechanical projects and all. So that there may be faulty, then that may be erroneous. So that kind of things we call it as noise, but disturbance are inherent, that external parameters it's being affected, not the variables, right? So this is the basic difference between these two. Okay. Just rewriting this. Okay. This is a mere representation of this. I'm not going into detail. Just writing this equation in terms of how we write it for error. This will be y minus r. So y will be in terms of h into g, g into h minus r. So this has been written in terms of that. So if you have any doubt, we can see that later. And what else is important? Okay, just go through this. This is an important topic where what is the difference between the open loop and closed loop? What you can expect in open loop, what you cannot in open loop. This kind of differences they have spoken here. Okay, we have already defined this table when we are seeing the steady state error, right? So I hope you all familiar with this. Right. Anyone? Sorry.
Yes, this PID one. No?
Yeah, Ram Session took this PID controller.
Yeah, he took actually PIT 2 weeks earlier only. He actually discussed this thing, and
Yeah,
I
he
was like,
followed that
this is
actual
part of
schedule.
yeah.
There was some paradox, no? So after that, he thought like he can continue with the next week. That's why he took that.
Actually, after paradox only he taught that.
Right, right. Okay. So I hope you know PID, or if anyone wants me to repeat it, I can repeat now.
It's like integral and derivative, like what we done in our Laplace transform.
Right. So anyone else wants me to repeat this?
Ma'am, can you tell briefly?
Okay, right. I will repeat it. Okay. Good. So as I said, we used to have, if I want to design a controller, I will design a controller gain here. Okay. So this is my output, my input, and feedback. This will go back. So this I am calling it as controller, and this is the plant of my system. This is the feedback. Okay. Right. When designing a controller, the purpose of the controller is to add or remove the gain of the system so that we can get the desired step response. Desired output response. For example, before introducing a controller to my system, if my input is one step, say a step input of one, and my system is giving something like this and not getting into the one, really it is around 1.2 forever. After reaching the steady state also it is like this is case number one. If I say case number two, the same input I'm giving, but I'm getting some output like this. This time also it is not going into the steady state properly. Case three, okay. So it is reaching the output, but it takes a longer time, and also that output oscillates a lot before it reaches a steady state. So these are some three cases I'm considering for now, but I want some perfect output that tracks my input properly. So for this is the objective. This is my objective. I want to design a controller for all these cases so that I will get some response like this, some perfect world response I am expecting like this. So how are you going to design a controller, and what is the way you will consider a controller to be? So we have the information of the system. We know the transfer function of the system that involves zeros and poles. Now we are going to change the gain of the system. Gain in the sense, if there is no zero, there will be some constant term in the numerator that we call it as DC gain. Right, some poles. Or after gain also there will be some zeros. Can also be there. No need. We are going to change this gain. Sometimes this adding a zero and adding a pole will also come, but for now I'm keeping it for simplicity. I'm going to change the gain. By changing this k gain, how well I'm going to change the system behavior. So will I be able to change this system behavior to this? This I am going to consider as B, case B. This is C1, C2, and C3. So how I'm going to design a controller so that I can push C1, C2, C3 to behave like B, right? Is it clear? Is the motivation is clear? If you understand
Yes, ma'am.
so far, just give a thumbs up.
Yes, ma'am.
Right. Okay, good. So now there are three things. We are starting with the simple thing. How we are going to start is, since I have this K0 and pole, this is the original system. Some numerical terms will come. I'm just considering the standard form. So now I say if I change the K to KC, how my system is going to behave. This is the first criteria. Second is I am going to place a pole, extra pole in the origin. So how well it is going to affect the system. Third thing is if I place a zero in the system's origin, how well is going to affect the system. These are all the three cases we are going to study. First one is gain constant. I'm going to change K equal to KC, some gain, some random integer. The second one is the adding a pole at the origin. So K will become K by S. Adding a zero at the origin, K will become KS, right? So these are all the three things I want to study. The first thing I included, no, this I am going to call it as P. This I'm going to call it as I. This I'm going to call it as D. Why? Because in Laplace transform, if I do 1, if I take a Laplace transform of 1, then it will give 1 by S. In Laplace transform, if I do a when it will add, okay, instead of this I will tell with this. Wait, let me tell this. Okay, good. This adding a pole, right? Adding a pole is to mimic, we are doing a integration. Adding a zero mimics, we are doing a differentiation. How we are doing this, I will explain it. Okay, so when you see this, I'm going to add one K is equal to KP, that we are calling it as proportional constant. Some random number, proportional. Previously I have kept it as KC. Now I'm calling it as KP, that there is no any difference. Okay, second thing I'm going to do is I'm going to put one gain KI, where I'm going to integrate this KI gain to T with respect to the time, for all the time the system is on. So if I'm integrating T, if you take a Laplace transform, you will get Ki by S. The third thing is I'm going to differentiate it, d by dt of Kd. This, if you take, this will become Kd into S. So these are all the three different control actions you can perform. Just adding a constant or integrating the system for all the time and see how well it behaves. And the third thing is differentiation. Why it is necessary? There isn't any space to write. Okay. Why it is necessary? As I said before, if I want to track this, but my system is like this. So this is the error we are getting, right? This we used to call it as steady state error. After reaching its steady state value, this is the error. For example, if this error is 0.1, let's take, okay. I'm supposed to get output as 1, but I'm getting 0.9. So the error would be 0.1, right? So if my goal is to make the system go to 1. So if I want to make this 0.9 go to 1, I have to make the output as 1. So this error should be bring down to 0. So adding what it makes to 0. Adding 0 would makes to 0, but doesn't make any sense. We cannot implement anything to naturally. So I am going to add some 0.0001 into 0.1. So this will nearly make it to zero. So that is what I'm calling it as. I'm going to make this as KP, where this KP gain is this 0.0001. That will push my system to behave in a way I like. So by adding this gain, I will make the system to go like this. There will still be error, but it's not very, it's very negligible, you can say. So your control objective will be achieved. This is one thing. So the disadvantage of using this is sometimes this error cannot be minimized further. Why? Because so if I get, if my original system behaved like this, if I can push this after implementing some gain, if I can push the system to behave like this, but this difference I won't be able to make at all. Sometimes it's based on the system behavior. So these are all the disadvantage of using only proportional gate KP. So at this time, what I will do is I will introduce some integral action also. This integral action will keep track of all the errors we have accumulated so far. So for example, the first iteration, this is 0.1. When I multiply it with 0.001, it will become something other reduced value, right? Some other reduced value, maybe 0.009, just randomly considering. So if you again multiply this with 1, so it will further getting reduced. This will take this, if I introduce this integral term, this will accumulate all the error we have achieved so far. Based on this will change the gain. So you will achieve better stability of controlling the system when you introduce this integral. Coming to the differentiation part,
Ma'am,
ah,
integration will basically like mark those values and see the area. Like the area will be very small. Is
okay.
it like I'm asking, is it like
No, no, not like it. It will add up the error so far for how long you are what to say, how long you are giving an input to a system. It will keep track of the error you are getting. So it will try to reduce the error like this exponentially down. So it will change the gain KIE based on this error nature. So if the error gets increased, it will tune the KI so that it will bring down the error. Instead of changing it simultaneously, we are making a history of errors. We are saving the history of error and how well the error is going down. You don't know in if you do a KP, if you multiply a KP, you don't know whether the error is getting increased or decreased. You don't keep track of it, right? If you are not saving or if you are not visualizing it. So this error term, KI term will keep track of those error. It will integrate those error over the period of time, then it will change the gain accordingly so that you can see a exponential decrease of the error. The disadvantage, there are disadvantages in all the things, right? The disadvantage of this integral would be it can increase the overshoot. For example, if the error is too much, the gain will also increase too much, so sometimes it will increase the peak, so it will take time to settle, or the deviation would be so large. That's where the differentiation comes for rescue. This differentiation will bring down the overshoot value. It won't make it go too much. Even your integral gain is too much, right? It will just hold the gain value or bring down the gain value, whatever value the integral part is taking it up. So, but this disadvantage of this value is this make the system sluggish sometimes. So you should be able to know what proportion you are using for each and every controller. How well you are tuning this KP, KI, KD depends in your hand. There is no predefined what to say, There is no book term for this, how you are going to choose a KP, KI, KD system, gains for your system. It's a trial and error method. There are some concepts like Ziegler-Nicholas methods for choosing this, tuning this KP, KI, KD. But for most of the simple systems, tuning by hand would do. You will know once you grasp those concepts, you will know based on the system behavior what you are going to change, what you have to change for the game. So the you should try to understand how changing each gain will change. For example, changing KP will do what, KI will do what. KP will, it's a proportional controller, right? So it will define a gain that is proportional to your error. If your error is large, this gain will also be large. If your error is small, this gain will also be small. Sometimes this won't serve the purpose. Sometimes this will give a constant steady state error. That's why we are going for the integral action. But integral action, it depends on the nature of the error or propagation of your error for a longer period of time. It doesn't depend on whether if the error increases now, it will increase, not like that. So I can explain this with an example. For example, if you are giving setting your AC to work in 24 degrees Celsius, right? It will be in 24 degrees Celsius when you set. So after some time, if the heat increases in the middle of the day, there will be too much sun, let's take. So the room temperature may rise to 26 degrees Celsius. So every time, for every second, the sensor is not going to check. It will check at a some particular period of time for every 5 minutes or every 10 minutes, for example. So all of a sudden, when it checks, it notice that there is a 2% in 2 degrees Celsius increase. So if I use only the proportional controller, I will say, so this becomes 26 minus 24, that is 2 degree. So my controller gain would be 1 by 2 if I design it like that. So it will be 0.5. So it will bring down the degree Celsius to into 0.5, 13, right? So now 24, 13. So this becomes a very large gap. So if I keep on doing like this, I might not be able to reach the 24 at all. This is the disadvantage of the proportional controller. So there comes the integral controller. If I include the integral and the proportional controller, what this integral controller will do is it will try to save this value for initially it is 2 degrees Celsius. Then it becomes 13 degree. The difference between this will be 11 degrees Celsius. So after that, I would have introduced some proportional, so that maybe, for example, 7 degrees Celsius difference. So this will keep track of it and add again. So that depends on the difference between these errors or difference of this error. So this will help us reduce the steady state error, but it may increase the overshoot. For example, this 2 degree and 11 degrees too much, right? So the gain will also be increased too much. So there will be overshoot. That is why using integral controller along with proportional may have this disadvantage. So here we will use a derivative controller, where the derivative controller will slow down this process. You won't get a overshoot, but the disadvantage if this is overdoing this derivative controller will make a system sluggish. It will take time to reach the steady state. So you should be able to play around with this proportional, integral, and derivative. Choosing a proper gain will give a proper output for your system. And there isn't any method that you have to do like this. No book written method. You have to tune it by hand. Any doubt in this?
So it's like we are not solving each and error every time. We are taking the track of record of errors, then we are solving it at last.
No, we will do it every time, but this integral controller will keep track of this history. If you use this integral controller, you will do in that way.
Okay.
So if you use only proportional controller,
Hmm.
see,
Yes.
uh, for an instance T, I'm starting my system at T. So you will give one
Okay.
input, one output you will get, right? At when T equal to 1, I am giving some 220 volt to my AC. and it is giving 24 degrees Celsius. I'm setting it to 24 degrees Celsius to AC, and it is 24 degrees Celsius. Let's take. Okay.
Yes.
After 2-3 minutes, it will reach 24 degrees Celsius. But because of some external disturbances, after 5 minutes, it goes to 26 degrees Celsius. My sensor is reading it as 26, but my set value is 24. So this is the difference, 2 degrees Celsius. So at all the instance, I am going to give a control signal by uh, analyzing my output. So this is every time controller, when there is a controller, it's a closed loop system. This is a controller, this is my plant feedback, and this is the input. Input will always be 24. But now
Input
the
is always be 24.
Ah, now the output become 26. So this will be given back as a feedback. So what this will do is, if you have only proportional controller in your system, if you designed only KP, no KI, no KD. So what this will do is, this KP will be changed so that the output will become a 24 degrees Celsius. So what
Okay.
value, if you set it as KP multiplied with this actual plant, will give you 24, that value it will take. It's a difference between the actual and your output sensor feedback. So the error always,
Okay.
right?
So here we can see how the feedback is working and it
Uh,
changes the value of KP. Okay,
yeah,
we
this
got it.
KP will be proportional to the error. If the error is too much, if this is instead of 26, if this become 30, the
Hmm.
proportional gain will also be increased. KP will
Yeah.
be proportional to your
Yeah,
error. That is,
the error value will also increase if
yeah, your gain,
yeah.
overall gain will be KP into E. So that this proportional will be
Yeah,
proportional.
1 by 6. For 30
Yeah,
degrees Celsius, it would be 1 by 6.
1 by 6. So it will increase accordingly. But if you have an
Yeah.
integral controller along with it, what this will do is, at the first instance, that will also behave as a proportional controller. There will not be any change, because at first
Yes.
instance the error is 0, right? 24, 24. Integral won't do any actions. At the second instance, what it will do is, it will see there is a 2% increase in the temperature, 24 to 26. So already there will be some proportional gain, and this integral controller will also add some gain. That is, it is integrating the value of error over the period of time. At first, it will integrate 0 plus 2. Right now it is considering it as 2, so it will generate some value that is proportional to, let it reduce the 2 degrees Celsius that it increased. After a period of time, I'm speaking about over a looping of time, 3 second, T4, T5, T6. After it goes, so this will keep track of all the degrees that is being differentiated from the output. So for example, after some time it might go to 10-degree difference between, this might go to 35, so this will become 10 or 11. So based on all these things, this will generate a control action based on that, based on the error, integrate over the period of time, not like proportional controller. At instance it is changing, right? Based on your error, it is proportionally it is generating. This is not like that. It will keep track of all the error. If the error being increased so far, this will be reduced so far. This will keep reducing it. If the error getting reduced, this will keep constant. There won't be any change in the integral gain, because the goal is to reduce the error, right? So somehow this is how it will make the error to come down as soon as possible. So bringing that error down as soon as possible is the problem here, that it is giving the overshoot.
Yeah, that's okay, fine. The only the last part. Wow, why it will give overshoot? Means in the integral part,
Mm-hmm.
we are tracking the record of all the errors.
Mm-hmm.
At instantly, it will just change it after some time, uh, like a time constant.
Okay. You are
So
asking
why
again.
why it will give overshoot? The only the last part.
See, it is accumulating the error. So after a period of
Yes.
time, if the error doesn't go to zero, the overall error will be high. So it is going to generate a control action that is also high. So this will increase the overshoot in the system. The output response will be abrupt.
Acha, okay. Yes.
Clear?
Yeah, yeah, yeah.
So then you can introduce a differentiation controller where it brings down this overshoot, not the system to respond in a very dramatic way, even though the error is not zero. It will take the system slowly, but without any integral action, if you introduce this differentiation alone, then it may make the system sluggish because it is bringing down the response, right? It is not letting the system overreact. So it may create a delay in the system. So using this gains, you should be very careful while choosing this gains.
Okay. Yeah, fine.
The thing you're asking, see, for if I'm doing like this, so even if it is 0.01, okay, this integral controller will add this 0.01 forever. For proportional controller, this doesn't matter. This is very small error. But this integral controller will keep track of this. So it will add up this. So after a particular time, it will reach to 1. After some time, it will reach to 10, 100. So this will create a imbalance in the system. That's why, so to make this, to accommodate to this change in the error, it is going to create a very big control action. So that will increase the overshoot of the system. Overshoot in the sense, it will be the output response will shoot, like go to the peak.
Okay, now I got it. So after accumulation of the save, like 10, 10, 10, 10, after 10 seconds, just take
Yeah.
an example, a time will come when the error will go maximum, means a significant value takes place and
Yeah.
it will
Right.
create problem. Yeah.
Right. Right.
For
It
that,
will
we
become a
introduce that differentiator part. Uh,
yes. That will
yeah.
pull down the that reaction. That it will slow
Proportion,
down the reaction.
proportion is over, integral is over, and now differentiation is left.
Yes.
Then the differentiation will, what it will do, it will not, it will
Let the
also slowly,
system
it will slowly decrease the error, not like drastically
absorb
it will
action
decrease. Yeah.
as integral does. So
Yeah.
So, ma'am,
yeah,
so basically, like this integral controller is just adding the values. We are checking at every time is it close to zero error, and
right,
by adding those small values, it becomes large at some time.
correct, very good.
So, ma'am, can you explain this again? Like, why can't we just change the proportional controller, like at
Oh,
every time? Why can't we again and again cancel that?
okay, right. One minute. So they put only I will okay, right here. So if I have a system, there is a controller, and this is the output, right? For example, if I'm taking a car example, same car example, my input value is 100 kilometer per hour. If I want to ride it in 100 kilometer per hour, but the speedometer is showing 35 kilometer per hour. I want to ride in 100, but the speedometer, the feedback speedometer is showing 95 kilometer per hour. Now the difference is 5 kilometer per hour, right? So what I will do is I'm introducing a controller inside so that it will generate a control action KP that is proportional to this value 5 kilometer per hour. So this proportional won't immediately make the system to go to 100. It will try to reduce the error. So for example, after doing one control action, I'm getting 99.8 kilometer per hour. Now the difference is 0.2 kilometer, right? So again, this control action will be generated into some value, KP proportional. There will be some, what to say, some difference in this 99.89 or something. It won't be perfect every time. So because of the physical nature of the system. So this error will never come down to 100. So this may create, it looks like this, but there will always be something like this, some deviation, minute deviation will be there. It won't be perfect at every time, I'm saying. There are systems that is perfect, but you won't make all the system perfect using this proportional controller. That's what I'm saying. So this is proportional to the error, right? So when the error gets increases, the proportion will also get increased. When the error get decreased, this gain will also get decreased. So based on the change in the error, the control action will also change. So you cannot expect the control action to be stable all the time, because when the error is, for example, if the input is here, when there is, if the output response at this instant is like this, my control action would look like this. If my output response is like this, a control action will also come down. If the output response comes down, it will goes up. So this is a proportional controller that it generates control action proportional to the error. So whenever the error changes, the gain is going to change. It won't come to a stable region, so that the error will also be stable. That's what I'm trying to convey. Is it clear?
Yes, ma'am.
Right. So that's it. You have to. The ultimate thing you can learn out of this is choosing proportional, integral, and differentiable gains or trial and error method. There are dedicated methods that you can study, but for simple systems, this would be helpful. Changing using trial and error would be helpful, but that affects the system behavior. So you have to be very careful while choosing these gains. You should know, based on the system's behavior, you should know what kind of controller you want to design. There are popular systems with only P controller, or you can do with PI controller. Some for some systems that overshoot won't happen. It would be after introducing some integral gain, it would come to a stable region. So PI is enough. Sometimes you would go with PID controller or PD controller. There are some what is this, UAV based systems are okay with PD controller. There are many papers with PD controller for unmanned aerial vehicle, the drones and all. So you don't really need every controller for every system. You should be able to pick up what you want. That if you start to solve some problems, or to start to study the nature of the output response of the system for a given input, you would be able to sense, okay, now the overshoot is too much, we have to introduce some D. Now the system is very sluggish, it is giving output response in a very slow manner, so I have to include some I. So this kind of trial and run you can do out of it. Okay, then here they have explained in mathematically how it is, what is a proportional, what is the integral controller. So this is what I'm saying. So here it might not go to this set point sometimes. So some constant deviation would be there, but you cannot take it back from using only proportional controller. We can solve some problems based on this, and I think it would be helpful for you. I'm looking for some possible problems. Give me a minute. All the problems is based on this 7 equals what? Okay. Now, you do, okay. We consider an example. I'm considering a mechanical system where it has this. Right. So I can write like this. Okay. I'm considering a mechanical system where M is the mass, F is the force, and B is that spring constant. Sorry, K is the spring constant, and B is your what do you call it?
Friction.
Friction coefficient. Okay, right. Okay, so how will you write a dynamic equation for this? So whenever there involves a mass, then it becomes the d squared x by dt squared. For any spring, it won't have any memorable actions, so it would be x into k. This would become m into this, and for it, your friction quotient, this will become b into d squared by considering this as x. The position we are considering it as x. So B will experience a velocity that is dx by dt. So the m into acceleration that I can represent d squared x by dt square, I can represent as x double dot plus your friction quotient with the experienced f velocity, and your k will experience this position will be equal to k into x, right? So if I write it in terms of Laplace transform, if I do Laplace transform for all these things, I would have m into s square of x of s plus b into x of s, sorry, s into x of s, right? bs into x of s plus k into x of s equal to f of s. So this will become x of s output by input. So x of s by f of s, it will be equal to 1 by ms square plus bs plus k. So this is the overall transfer function of your system. Right. Now, I'm going to give some values to the system. Let's take the mass of the system will be 1 and friction would be 10 and k would be 20. Spring constant would be 20 and a force equal to 1, let's consider. So this will become x of s by 1, then it will become 1 by s square plus 10s plus 20. S square plus 10s plus 20 to x of s is equal. F of s is 1, so I'm just putting 1 here. Right. So now, if we want to write this in terms of this closed loop control, then I would write it as R of t is equal to 1 by, or R of s is equal to 1 by s square plus 10s plus 20. The output would be y of s. If I consider feedback, I will say what feedback I'm using. Lift. Okay, this will become this. So if I plot the output response of this, how it will look like. So for that, we need to study the time response analysis of this. I'm just going to use all the concepts we have studied so far in this problem so that we can revisit that also. So this is in terms of a standard system, 2 zeta omega n s plus 20. So omega n squared will be equal to 20, omega n will be root 20, then it will become 2 into root 5, right? 2 zeta. If I do any mistake, let me know. It's equal to 2, 2 root 5, omega n is equal to 1, omega n is equal to 1 by 2 root 5. Okay, sorry, zeta will be. Okay. If anyone could calculate this value, let me know. What is this and what is this? One by 2 into root 5. It is similar to 0.22. 2 root 5 would be
4.47.
4.47. So the natural frequency of the system is around 4.47 and the zeta value is 0.22. So it is clearly a underdamped system. Right? So your response should look something like this. Not sure how the peak would be, but something similar to this. So when we simulate the system, then only we will get to know. So what could be this steady state or your final value? So for this, we can introduce a final value theorem to identify the final settling time of the system. So for that, if we want to find it for t tends to infinity, x of t, I'm sorry, x of s as you want to find, right? Not t of s. Then this will become limit s tends to 0, x of s into x of s. Then this will be limit s tends to 0, s into, what is your s of s? 1, sorry, s square plus 10s plus 20. Right. If I put s is equal to 0, it will become 1 by 20. So this is similar to 0.05. Yeah? Still be points. So your steady state value after reaching some point, this will become 0.05. Right? Good. But our set point we have given is 1. We are expected, the system is expected to give 1, but it is giving a response of something like 0.05. This is a very large difference, right? 1 minus 0.05 would be 0.95. It's a very large difference between this expected and the desired response. So we have to design a controller so that this will bring this 0.05 to 1. So this is the goal of our design. That's how we want to design a controller that will compensate these errors. Right? So for that, we will first write a closed loop transfer function. First, the open loop transfer function is a square plus 10s plus 20.
We
Then
have to make this 1 or 0, 0.04.
no, it's giving a steady state value as 0.05, but my set point is 1. So if I want to have a good tracking or regulatory system, I want to bring this steady state value to 1 so that the error is equal to 0. Now the error is 0.95, it's quite large, right?
Yes, okay.
Right. So if I find the closed loop transfer function, it will become 1 divided by s square plus 10s plus 20 plus 1, considering unity feedback system. Right? So this will become 1 by s square plus 10s plus 21. So 21, this will become, okay. Right. Instead of this, if I'm considering, previously it was like this, R of s, G was like, G was there, but now I'm introducing a controller. I'm going to design a controller GC. I don't know about that GC yet, that I'm going to design, right? So just introducing those terms. I don't know what to do with that GC, whether it should be proportional or it should be integral or a combination of those. We don't know about it. We are yet to design that, right? So if I introduce this controller, then I'm writing a closed loop transfer function. Then now how it will look like? This will become GC into GC by s square plus 10s plus 20 divided by s square plus 10s plus 20 plus GC divided by square plus this, all the term will come, this both will get cancelled. This will become GC divided by. Clear? Right. Now we are going to find what this GC is. That is the criteria, whole point of the system. So for now, I'm going to give a, actually we have simulated this out so that I know what to change. Since it is a trial and error method, we
Ma'am,
have done.
it will be 21 in denominator instead of 20.
That is for the normal closed loop transfer function I have written here. This is a GC. We don't know that, no? It's only GC. GC into 1. It's not GC plus 1. These both are in cascade, right? So this will become GC into 1 by s square plus 10s plus 20. So this will automatically become GC by. Right? So the denominator would be 20 plus GC. Is it right?
Yes.
Right. Okay. So we have simulated this in MATLAB. So we can also show you in the next class that how we can do this in MATLAB. So I'm randomly taking this value as it worked for me. So based on trial and error, you can do it by hand also. I'm just keeping KPS 300, sorry, GCS 300. Just common proportional controller gain. So if I take this, this will become 300 divided by s square plus 10s plus 320. So if you simulate this, you will get a response similar to this. If one is my set point or this is the reference input I'm getting, my system would give a response like this, right? It's similar to one, but it is not one, around 0.98 or something it gave. So I can say this is a good design. I don't want to make this error go down better than this. This is enough for me. So I'm stopping with this proportional controller. So for this gain. So likewise, you have to tune the gain, do a trial and error method to make the gain come to a proper number where your output response will be behaving in the required way. That's how we design the controller. Right? Similarly, in that, if you do by hand, it will be tedious. Similarly, in the MATLAB, you can see by adding a PD derivative term to this. If I add a derivative term, how this is bringing down, how well the sluggishness is. Or similarly, you can add I term and see how quickly it is coming to the set point, but what is the maximum overshoot it is giving based on your. So you can do all this trial and combination with this, and you can find how well it is suiting for your system. Right? We will wrap this for now. We can continue this on Wednesday. And meanwhile, if you have any doubt in your week 4, week 3, any questions you have come across, any doubt if you have, you can ask me. We can discuss on that for 20 minutes. Any doubt if you have, you can ask me. Because we have solved so many problems. So I don't think any different problems we can solve. There is any new concept or new thing. I can redo the problems, that is fine with me. Otherwise, if you have any doubts, you can ask. Any problem with the assignment till week 4? Anything you don't understand or you want me to revisit? No, right? So I will be here till 8 in case if you have any doubts. Otherwise, we can wrap up. Should I solve 1 or 2 problems in week 4 or anything?
Ma'am, can we solve practice assignment 5?
Practice assignment 5. Yeah, we can do. Right. I will open that and okay. Week 5 practice assignment. Okay, the first order system has a transfer function You can open it. I will just write the solution. We will just solve for the solution. I'm not going to write the question. First order system has the transfer function with the PI controller. The closed loop system has the characteristic polynomial. You can compute the values of Kp, Ki. Right. PI controller closed loop characteristic equation they have given. This will become Kp by S plus 2. Okay, good. Okay, right. The first question is they have given a transfer function. It's a first order system they have told that then I know the G of S. Then they say they are going to use a PI controller. So your GC of S would be KP for P, KI by S for S, because in time domain this will look like KP plus KI into integral E of T, E of dt plus KD into d by dt of E of T. So taking an inverse Laplace transform, Laplace transform, you will have this. Since there is no D, I'm just going to um, rule out this, keeping only this first two terms. Okay. Right. Okay. Now I have these two terms. So if I write it in terms of a closed loop equation, R of S, GC, G, Y of S actually it is H, right. So this two will be in cascade, so you are going to multiply it. So G of S into GC of S, your loop transfer function would be 1 by S plus 2 into Kp plus Ki by S. This will be inside 4. So this will become Kp by S plus 2 plus Ki by S into S plus 2. This is going to be your G of S into GC of S. Okay, good. If I want to write it in terms of a closed loop, they have also given the closed loop system unity feedback has a characteristics of this characteristic equation that closed loop systems pole they have given in terms of characteristic equation. So I want to find the closed loop transfer function of this. If I want to find the closed loop transfer function, this will become Kp plus Kp by S plus 2 plus Ki by S plus S into S plus 2. Okay, I will simplify this and write. This will become Kps plus Ki, right? S into S plus 2. Am I right or did I make any mistake? Let me know. Divided by 1 plus Kps plus Ki by S plus 2. Ki, good. Now this will become Kps plus Ki divided by S square plus 2s plus Kps plus Ki. Then Kp into S plus Ki divided by S square plus 2 plus Kp into S plus K. Now we have simplified this closed loop transfer function. They have given some information about this closed loop transfer function. That is a characteristic equation, which is the denominator. So they have told something is above, but denominator they have given S square plus 3s plus 4. It is given in the question. This is equal to Kps. Something happened. Okay, the pen is not writing. Kps plus Ki divided by S square plus 2 plus Kp into S plus K. So equating this to, you would get 2 plus Kp equal to 3, Ki equal to 4. So Ki is straight away 4, Kp would be 3 by 2, right? You know the controller gain. So this is your overall controller gain. So that is what the question is. So Kp would be 1 and sorry,
Ma'am,
3
KP
by
will be 1, 3 minus.
oh minus. Okay. Okay, right. 3 minus 2 equal. Alright. Kp will be 1 and your Ki will be 4. Right? Good. So the second question is, this is a standard question. You would expect this in all the control systems question. So consider a system. They have given a system in the figure, control system in the figure, where they have given the choice of a controller. First controller is only KP, proportional. Second controller is proportional plus integral. Third controller is PID. PID, right? No, that is also a proportional integral controller, but with
Only PID.
similar
Yeah.
terms. Yeah, PA. Okay. Right. I will just rewrite this system, giving an R di. This controller, we are going to find what it is. This is 10 by s plus 1 into s plus 10 y beta. This feedback also, I think they have given. Let me check one. Okay. That's it. So now, what are all the information they have given? They have given beta is equal to 1. So I'm just going to replace this. Why do you want to complicate it? Right? Beta equal to 1. It's in the question. And some controller they have given D1, D2, D3 that you can see from the question. Right. So choose a controller and find the range of parameter values that will result in type 1 system. So this is another information. The system should be type 1 because only one pole should be at the origin. Okay, next information is non-zero steady state error of less than 1. So your steady state error should be lesser than 0.1. It should not exceed 0.1 for a unit ramp input. These are all the information that can extract from the question. Right. Now what we are going to do with this information, we are going to relate the terms we have studied so far, and we have to find what controller that suits it. They have asked that what controller, if you include it here, will give a steady state error for the system that is lesser than 0.1. That is the question. Okay, for that, we have to first find you just have to first use your intuition first. The first thing is, if you take a proportional controller, how the system is going to work, and the second it has proportional integral and proportional integral again, but it is in terms of s square, right? So you have to choose wisely. Think we will pick first KP. Okay, we'll just go with the traditional method. They have told that it's a unit ramp input, so I am going to find the velocity error constant. So in that table, if it is a step, it will corresponds to 1 by 1 plus Kp. If it is a ramp, it is 1 by Kv. If it is a for steady state error. If it is parabolic input, if it is a 1 by Ka, it belongs to the acceleration. So I'm going to find the velocity error constant, use those formula for that. So Kv can be found using the formula limit s tends to 0, s into your g of s, right? So if I pick the first controller, that is Kp d1, this will becomes limit s tends to 0, s into Kp. There is no term to um, eliminate. Then this will become 0, Kv becomes 0. Then your steady state error would be 1 by 0, it will be infinity. The error would be too large. So you cannot choose this first controller. So removing that, we are proceeding with the second controller, that is KPS plus KI divided by S. This is the second one, right? So if I put it here, KV is equal to limit S tends to 0, S into KPS plus KI by S into your G of S, that is 10 by S into S plus 1 into S plus 2, right? Because here the forward gain is GC into G, right? That's why I'm writing both for this finding this KV. So this will give you this S and S will get cancelled when you put S and S will get cancelled, right? There will be an S. If I take a S out of it, this will become KI by S into 10 S into S plus, sorry, 1 plus 1 by S will become 1 plus 2 by S, because there is a term here down in S. I want to cancel it out. If I do all these things, this will become KT plus 1 by 0. Uh, if I put 0 here, what it would be? Am I missing anything out here? This should work, right? Anybody could find anything? Put zero here, it will go to infinity. That is not what we want.
I have to see that one. Then
Yeah.
what? First one is your infinite. Then D2.
This will become infinite, right?
Yes. Ma'am, it's 10 upon S plus 1 upon S plus 10. Okay, but 1 S will also.
I couldn't find what mistake I'm doing here. Anything by zero infinity, then this will become infinity. It won't give a finite answer. But we need a finite answer for this. Why it was not working?
Ma'am, can we take S common from denominator and cut both the S?
There is no there is no S in numerator, no.
Written it correctly, right? If I put a replace this with, oh, okay. Okay, there is a mistake. There is no S here, right, in the question. I have written in, I have, sorry,
Yeah, there is.
then it,
Oh, you have added one
yeah, it,
multiplied one.
yeah, by
Yes.
Ma'am,
mistake
but
I have.
it is a unit ramp input. Won't they run by S?
Won't they?
It's unit ramp input. So
Okay.
won't we put 1 by S?
Haha, that is, you will put 1 by S when you write in terms of steady state error. I am writing it in terms of KV. So it won't come.
KV is different. Yeah, KV is different and SSE is different.
SSE for the ramp input is different. The term that is only in the denominator, we are taking that 1 by KV. Instead of that, we are considering it as KV. That is different. Here, this KV is defined for the ramp input only. So if you have ramp input, you will get KV. Otherwise, you won't get. That steady state error is common for all the input. You can put any input in that. right? In that steady state error equation, if you put RAM, you will get this 1 by kV, right? Where 1 by kV is this 1 by limit of s tends to 0, s into g of s. You will get something like this.
Yes.
If you are not convinced with this, I can go to that and show you.
No, it's okay, I guess.
See, for ramp input, this is 1 by kV, that is SSC for type 1 system I'm considering. I want to show that. Okay, it is not here. Okay, good. Now we are taking this. Right. Distance. Good. Now I will get, if I put S is equal to 0, this term will go to 0. Then I will have Ki into 10 divided by 002, right? This will become 10 Ki by 2. Some some finite value I will get. Okay, I have this confidence. I will come back to that Ki later. Okay. Now we will try with the D3, that third option. Kp s squared plus Kis plus K2 divided by s squared shows. So this Kv becomes limit s tends to 0, s into Kp s square plus Kis plus K2 divided by s square into 10 into something. What are all the factors? So here itself, you see, if I minus, take out one yes and one yes, there is a s here. So the overall kV will be infinity. So if I find a steady state error, this will be 1 by kV. It will become 0. But we want a steady state error lesser than 0.1. Not it is 0. Actually 0. It was not mentioned like this. So if we see if this is lesser than 0.1, we could go with this choice, some finite number. In that question, that's why they have mentioned non-zero steady state error. So you should not consider this since it is lesser than 0.2. Okay, right. Now we know the steady state error ESS should be lesser than 0.1. What we got so far is kV, we know it's 0.1. So E of SS will be 1 by kV is equal to 1 by 0.1. This will give you 10, right? Oh, okay. Why am I getting confused with this? They haven't mentioned anything for KI, right?
Into na KI, I guess beta is 1. And no, there is no mentioning of KI.
KI it was not mentioned anywhere.
It's only told that that will result is in a type 1 system with a non-zero steady
Mhm.
state and error non-zero steady state error of less than 0.1 for unit ramp input.
Okay. This will be KP plus KI into 10 divided by S into S plus 1 into S plus 10. Give me a minute, okay? KP plus KI plus S into S plus 1 into S plus 10. Okay, I think I made some mistake. Um, I don't want to confuse you. I can solve this later and get back to you with the proper answer. Okay. I
Yeah, fine,
couldn't
ma'am.
where I
We
made the
can do.
mistake.
We can do another question.
Right. This is until 10. Oh, I think this is the entire question. There isn't any question other than this. Okay. We'll work out on this on Wednesday. I will start with this. Okay. Wednesday, I will start with this.
Yeah, fine.
Right. Thank you.
Ma'am, don't we have class on Monday?
Sorry. Monday. I will start off with Monday. Okay. I thought
Yeah,
today.
we do have class on Monday. Yeah.
Yeah.
On Monday we can carry on.
Right. And meanwhile, if you have any doubt, any questions, just post in G space. I'll try to answer them. I will prepare that
Yeah,
also. That
yeah,
will be easy
fine.
for me to explain it to you within this time.
Yeah,
Okay. Right.
yeah.
Thanks.
Good
Thank
night,
you,
ma'am.
ma'am.
Thank you.
Thank you.